Okay, good afternoon. Welcome, everyone. We are delighted today to be the host for the Shaw Prize Lecture in Astronomy. We have this year's winners and, in fact, last year's winner with us today as well. My name is Andy Cohen. I'm the director of the Institute for Advanced Study, the host for today's lecture. We will hear from all three of this year's laureates, telling us about fast radio bursts. And then following, we'll have an opportunity to take questions from the audience for them. Before we begin today, it's my great pleasure to introduce the provost of the Hong Kong University of Science and Technology, Yi-Ke Guo, who will introduce today's lecture.
Thank you, Andy. Thank you. Good afternoon, colleagues and students. It's our great honor to have the Shaw Laureates in Astronomy 2023, Professor Marcel Baylis and Professor Duncan Lorimer and Professor Maura McLaughin. And they're with us today to share their award-winning research discoveries. This is also a wonderful moment to celebrate the 20th anniversary of the Shaw Prize. The Shaw Prize Foundation was established in 2002, and Mr. Ron Shaw, a visionary philanthropist who strongly believed in the power of the knowledge. The inaugural Shaw Prize was presented in 2004. It gave out 3 awards every year in astronomy, in life science and medicine, and also in mathematics science. Regardless of the race and nationality, gender, and the religious belief, the Shaw Prize honors individuals who are active in their respective fields and who have recently achieved a distinguished and significant analysis, who have made outstanding contributions in academic and scientific research or applications, or who, in other progress, enhance the quality of life and enriching humanity's spiritual civilization. HKST takes pride as one of the partners, together with CUHK and HKU, to witness its success over the years. As we gather at the moment, I would like to thank the Shaw Foundation for bringing us 3 distinguished scientists to our campus. Let me introduce you to them. The first is Professor Marcel Baylis. Professor Baylis is currently Director of Australian Research Council Centre of Excellence for Gravitational Wave Discovery. And he received his PhD in 1990 from Australian National University. He founded the Centre of Astrophysics and Supercomputing at Swinburne University of Technology in 1998 and served as a director for 12 years. He's a fellow of the Australian Academy of Science. Thank you, Mr. Baylis. The second is the Professor Duncan Lorimer. Professor Lorimer is currently Professor of Physics and Astronomy and Associate Dean of the Research at Eberly School of Art and Science at West Virginia University. He obtained his PhD in 1994 from University of Manchester. After graduation, he served his alma mater as a lecturer from the 1994 to 1995. He was a postdoctoral fellow at the Max Planck Institute in Radio Astronomy in Germany from 1995 to 1998, and then Cornell University, USA from 1998 to 2001. He was a Royal Society Research Fellow at the University of Manchester from 2001 to 2006. And Professor Lorimer has been with West Virginia University since 2006, where he was assistant professor, associate professor, and now professor. He's a fellow of the Royal Astronomical Society and the American Physical Society. Thank you, Mr. Lorimer. The third speaker is Professor Maura McLaughin. Professor McLaughin is currently Eberly Family Distinguished Professor of Physics and Astronomy and the Director of the Center for Gravitational Waves and Cosmology at West Virginia University. She received her PhD in 2001 from Cornell. He was in the NSF Maths and Physics Science Distinguished Research Fellow from 2001 to 2003 and the Research Associate of the Georgia Bank Observatory from 2003 to 2006 at the University of Manchester. In 2006, Professor McLaughin joined the West Virginia University, where he was successfully assistant professor, associate professor, professor, and then now Eberly Family Distinguished Professor. He's a fellow of the American Physical Society. Thank you, Professor McLaughin. The topic of today's lecture is the discovery and the significance of fast radio bursts. Without further ado, please join me in giving a big applause to thank all our three distinguished guests for guiding us through their fantastic and scientific journey. Thank you.
Thanks very much for that warm introduction. It's a great honour to have received the Shaw Prize and also to be presenting it to everybody from enthusiastic young school students, hi Esther, to Nobel laureates like George here. So we're going to give a talk in 6 parts, and I'm going to start and then pass over to Professor McLaughin and then over to Duncan, and then we're going to go around the loop again. So the title of our talk is The Discovery and Scientific Potential of Fast Radio Bursts. And this is a story that actually goes back many years, but my job in my first chapter is to tell you about the universe and its scales and the kind of entities that exist in it. So some big astronomy questions. We don't study astronomy because we like making pretty pictures of space. We're actually physicists that are trying to understand where we are in the universe, how big the universe is. And so there's some questions that fast radio bursts actually touch on, like what is the size and age of our universe? How many atoms are there in the universe? What are the laws of physics that govern the universe? And with the students this morning, we learned a little bit about general relativity. And what classes of objects exist in the universe? You've probably heard of pulsars and quasars, planets, stars. We're going to learn a little bit about those in the next few minutes. So chapter 1, if you like, is our universe. So the scale of the universe is difficult for us to comprehend. We're on the Earth. We know that the Earth is about 40,000 kilometres in circumference. In fact, that's how the metre was initially defined. The French decided there would be exactly 40 million of them, 40 million metres from the North Pole all the way to the South Pole and back again. But how big is the Earth? What we're looking at here is one of the most famous astronomical objects. It's the planet Saturn. It has these beautiful rings that you can see, and I'll put Jupiter right next to it. In reality, Jupiter is so far away that if I showed them both on the plot, they'd just be dots. So a lot of the things you're going to see in this talk are a little bit magnified, so you can actually understand them. The spatial scales in the universe are so large that it's disappointingly how small everything is. But if we could put the Earth on the same scale as Saturn, it's actually quite revealing how puny our planet is. So that little blue dot there that you can see is actually the Earth. And the Earth, it's about 40,000 kilometres around. But you can see how big Saturn and indeed Jupiter are. And in fact, that little dot that's next to the Earth is actually our moon. And that little red thing is actually Mars. And the big red thing is the sun. And you could actually fit 1 million Earths inside the sun. although we are denser than the sun. And we can just fly up here. You can see we don't even make it to the span of Saturn's rings. Jupiter, apart from these beautiful patterns, is also larger, much larger than the Earth. And then there's the sun. So the sun is about 700,000 kilometers in radius. The Earth is less than 7,000 kilometers in radius, so we could actually fit 1 million Earths inside the sun. So on solar system scales, the Earth is very, very tiny. But the sun is not actually that big a big a star in our galaxy. There's a very famous star called Rigel, if I've pronounced it right. It's one of the brightest stars in the night sky, and it's actually a blue supergiant. And although the sun looks as though it's comparable, if I actually zoom out a bit, you'll see this is a camera trick. And this is our sun, and this is Rigel. Rigel is about 80 times the radius of the Earth. And it's so much brighter. It actually burns its fuel 100,000 times faster than the sun does. And it's going to end its life in a spectacular explosion called a supernova explosion and leave behind a very exotic sort of star called a neutron star. And we're going to need these a little bit later in our talk. These other things that are hovering around here, these are actually other galaxies. They're collections of stars like the Milky Way. And this one in particular, the Small Magellanic Cloud, has a very special place in our story. And Professor Lorimer is going to tell us about a special star that was discovered behind it. So these are some facts about Rigel. It's about 20 times as heavy as the sun, 80 times its radius, and importantly, it's 20,000 degrees. Our sun is only about 6,000 degrees, so this is about 3.5 times the temperature. And the amount of light you get from the surface of an object is proportional to the temperature to the 4th power. So this star is radiating about 100,000 times what the sun is. And it's a sort of a bit of a naughty star. It's living its life very fast. It's going to die young. And instead of living for like 10 billion years like our sun will, this star is going to blow up only in about 10 million years' time. So instead of 10 billion, it's 10 million. And when it does, the poor atoms in the core of this star, which are happily well separated by their electron clouds, are going to be compressed so much that the poor protons and electrons will no longer be able to withstand each other, and they will form neutrons, and we'll be left with a star composed entirely of neutrons, and something called a neutron star will result. We've actually seen the creation of neutron stars in our own galaxy, and in fact the Chinese astronomers back in 1054 AD observed this star blow up. It's a special remnant called the Crab Nebula, and at the heart of the Crab Nebula is a neutron star that's rotating 33 times a second. Or has it got a 33 millisecond period? I think it's a 33 millisecond period. Luckily, I've got some pulsar experts here I can call on. And it's giving off so much energy that it's lighting up this nebula. And the luminosity of that neutron star is about 100,000 times that of the sun. It's not going to stay that luminous for very long. It's rapidly losing its energy. And this supernova remnant is actually expanding and will dissipate eventually into our intergalactic medium. On the right is the fate of the sun. This is what's called a planetary nebula, very beautiful. And right in the middle you can see there's a little white dot. That's actually something called a white dwarf. That's actually the ashes of a star, which you might think would be black, but they're actually so hot that they're glowing and they're giving off blue light at the moment. And then over the course of the next billion years or so, they will cool down and eventually become a very dead star with little astrophysical consequence. So this is kind of what we're interested in today. These are neutron stars, and you can see it has a beam of radiation. We're going to learn a bit more about that later on. Next to it is what's called a black hole. This is about the size the black holes that the LIGO gravitational wave detector first discovered, when two of those ran into each other and caused space-time to shake in such a way that gravitational waves were detected from the first time. And in fact, one of the recent Shaw Prize winners were for that discovery. But these neutron stars and black holes are actually kind of tiny. The diameter of a neutron star is only about 20 kilometers. And if we compare that to a white dwarf, you can actually see that, if we can find the white dwarf, lost my white dwarf. Wait, there we go. It's actually fairly tiny. So a white dwarf, these are the ashes of a star like the Sun. It's probably about 20,000 kilometers across. The neutron star is only 20 kilometers across. So it's a tiny, tiny object. And you can see that it's almost insignificant. And that's because it's only about the size of Hong Kong compared to the size of the Earth. So stars live in objects called galaxies. And this is a picture of the nearest kind of major galaxy to the Earth. It's called the Andromeda Galaxy, or M31. And we think we live in a galaxy that looks a little bit like this one. Unfortunately, we're in the middle of it. So it's hard for us to get beautiful pictures. And we can't just send out a space probe because the distances involved are so great that the space probe would never even sort of move more than 1 pixel on this diagram. So what's the shape of these galaxies? This is an animation showing where the young stars in the Milky Way reside. It's a very thin pancake. When galaxies form, they're spinning, and they have no reason not to collapse to a dot except for rotation. And it forms these disk-like structures. So galaxies have a central bulge. Many times they have a bar, like our galaxy, and then these spiral arms. And we live about 2/3 of the way out from the center of the galaxy, orbiting the Sun. Our Sun takes about 225 million years to do a complete orbit of our galaxy. And there's about 10 to the 11 stars in our galaxy. But our galaxy is only one of about 10 to the 11 that inhabit the universe. And some galaxies are kind of boring shapes, like this elliptical galaxy. It has a similar number of stars to the Milky Way, but instead of forming a pancake that helps us create stars, there's only one wave of formation in these galaxies, and they're often called red and dead. And they don't have many neutron stars being born, so we don't like them. Nearby to us are the beautiful Magellanic Clouds, and if you go into the Australian outback and look out into the sky, you can actually clearly see these two blobs. And they're 100 million to a billion stars. This is the small cloud, which is smaller than the large cloud, which is this one over here. So the naming convention is very wise. And then this dot here is actually not one big star. It's actually about a million stars in a swarm called a globular cluster. And shortly after the universe was formed, lots and lots of these globular clusters were formed, but they're quite small compared to galaxies. And in these galaxies, there are stars being born today, and they're creating neutron stars. And that means people like Duncan, Maura, and I love to look at these nearby galaxies because you can see neutron stars in them. And then the final bit of my talk is just to give you an idea of scales in the universe. So each one of these dots actually represents many, many galaxies. And when the universe was formed, it was very smooth to about 1 part in 100,000. But because of the growth of these small perturbations in density, as it expanded, it locally collapsed to form galaxies. And you get these beautiful filamentary structures appearing. And it's very hard for astronomers to study what's between the galaxies. Because when photons travel through interstellar space, they come across ionized material. These are sort of single protons and electrons, and light just sort of goes straight past them, and it has almost no effect on visible light. So for many years, we didn't know much about the density of intergalactic space because optical light would mean that you couldn't tell what was actually between them. So astronomers for many years have been searching for what they call the missing baryons. And if you actually look at how much material is in galaxies, we kind of understand it, but there's a whole lot of protons and electrons kind of missing, and it's been very difficult to study intergalactic space. But luckily for you and for us, there's these wonderful things called fast radio bursts that we'll hear about shortly from our colleagues. We are actually radio astronomers, we're not optical astronomers. Most of our radio telescopes don't make very nice pictures of the sky, they're kind of blobby and noisy, but there's a beautiful new telescope in South Africa called the Meerkat. It's 64 state-of-the-art dishes, and because it has so many dishes looking at the sky at once, it can learn about the different spatial scales that make an image. And it made an image of the center of our galaxy, and you can see there's this amazing ball of glowing gas. At the heart of it, there's a supermassive black hole, and that's really a topic for another conversation. But there's gas swirling around the black hole. There's lots and lots of young stars blowing up and leaving behind supernova remnants. And if you look really, really carefully, and I always lose this, that is actually a supermassive black hole ejecting jets of material far beyond our Milky Way. And so you can see amazing things with radio telescopes that you can't see with optical telescopes. This is a picture of what I would call a conventional radio telescope. It was born in the early 60s, just before me. And between us, Duncan, Maura and I have spent a great deal of time on level 2 and 3 of this building. And indeed, some remarkable discoveries have occurred while we've been sitting in there. There's a type of radio star. When they first were doing radio astronomy, they didn't actually know what the sources of the radio emission were. They knew there were these funny things that were very spatially small, and it turned out they were quasars. And this is a model of a quasar. It has a disk of gaseous material spiraling into a black hole. It gets charged, causes magnetic fields that drive these jets of emission. And this is actually a real picture of a supermassive black hole spewing out jets, and this is our kind of model of what's going on. One thing that's interesting about these sources is that at the core they have such bright emission that's so small, it actually twinkles. And it's that twinkling of these radio stars that led to the construction of a radio telescope in England. And I'm going to hand over to Professor McLaughin to tell us about the transient radio sky that was motivated by the twinkling of quasars.
Thank you, Matt. Thank you. Okay, there it goes. Yeah, thanks for that nice introduction. So I am going to tell you the next part of our story. So, as Matthew mentioned, these quasars are radio sources. There's a black hole that is accreting matter and giving off radio emission. They're very far away, so they look very tiny. And as Matthew said, when you have a tiny thing, it does something called scintillates, or twinkles. And so Jocelyn Bell, and I'll get more to her on the next slide, but she was a grad student in Cambridge, UK. And she built and used this radio telescope with her advisor, Anthony Ewing, and her project was to look for the twinkling of quasars, or quasar scintillation. So she was happily going along, doing her PhD research on this quasar project, and she found something else very unexpected. So here's a picture of Jocelyn. She looks very happy, and she's very happy because she had discovered a really remarkable thing. So let's look at the top plot here first. So back then, intensity from a radio telescope was recorded using something called a chart recorder. To the young people in the room, this is going to seem just like completely unbelievable. But they actually had a machine with like paper, right? So a big like ream of paper. And the intensity of the telescope mapped, is there a little, yeah, here we go. High, when it went up high, that means there was something bright. And so they would observe the sky, and as the sky went overhead, this little pen would record the intensity of the radio emission on the sky. And so Jocelyn spent her PhD just with reams of paper, looking for quasars that were scintillating, right? And a scintillating quasar would look like a rise in intensity and a decrease in intensity on pretty long time scales. Okay. And one day she came across something, she called it a bit of scruff. And if you haven't heard Jocelyn speak about this discovery, you should go onto YouTube and look for Jocelyn Bell's discovery talk. She gives an amazing talk about this discovery. But this is what she saw. She saw this little thing right here, right? So a signal went up, went back down, something is there, right? Some kind of radio emission. She didn't know what it was. It looked kind of like interference. So interference is what we call stuff that's human generated, right? So stuff like TVs or other kind of like radio emitting devices. So it looked kind of like this interference, but not exactly. And Jocelyn could have easily just said, hey, you know what, like that's not what I'm looking at. I'm looking for quasars and move on, but she didn't. She wanted to find out what this was. She didn't know, and so they had to do things a little bit differently. So this was in August of 1967, and it took them until November to speed the chart recorder up. So she looked at this and she said, I think there's some really fine structure here, right? So short timescale structure, and we want to resolve it. So they sped the chart recorder up so it would record data much, much faster. And when she recorded data much, much faster, she saw this. So there were these periodic blips. The intensity is flipped. So these negative going blips, that's actually bright. That's bright radio emission. There were these periodic blips, boom, 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 boom. And they were at exactly a period of 1.3 seconds. Extremely periodic. They went back. They looked at the same position on the sky again. They saw the exact same thing. Boom, 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 1.3 seconds. The first one of these was actually nicknamed LGM1 for Little Green Man 1. And the reason they called it that is that this is a very short period. And for something to make a period that short, it needs to be very small. And they didn't think there were any stars that could be small enough to make something with that short a period. So initially they thought maybe this is aliens, maybe it's something that we haven't seen before and we don't understand. So this was very exciting. Soon they started finding more of these though, all over the sky. And they thought, well, this can't really be an alien signal. There's too many of them, they're all over the sky. They thought it was from some very special kind of star. And Matthew talked about white dwarfs and neutron stars. And they still weren't quite sure until 1968, when they discovered a pulsar, a radio pulsar, which is what, I never even said that this, did I say this was a pulsar? This is a pulsar. This is the discovery of pulsars. This is a radio pulsar. They found one of these things, one of these periodic sources, at the center of this Crab Nebula that Matthew talked about before, right? And so once they found one of these right at the center of this nebula, they knew. These are stars that are born in the supernova explosions of massive stars. So they knew that pulsars were neutron stars born in supernova explosions. This was a really important moment in the history of radio astronomy and obviously for our understanding of radio pulsars. Okay, so let's talk a little bit about what pulsars look like. So pulsars, this is a little cartoon of a pulsar rotating. You can see emission coming from the north and south magnetic poles. And pulsars are kind of like lighthouses. As they spin by us, every time this beam passes our line of sight, we will detect a pulse. So the thing that Jocelyn saw was oh, yes, I don't know if I can be trusted with this, but I will try. The thing that Jocelyn saw, that 1.3 second period object, was a neutron star like this spinning at a period of 1.3 seconds, and every 1.3 seconds a radio pulse was detected. So these objects spin from about 1.4 milliseconds, so that's like 700 some times a second, so really, really fast, up until tens of seconds. They have huge magnetic fields, trillions of times the magnetic field on the Earth. They're very small. The radii are about 10 kilometers. So you could fit a pulsar inside Hong Kong, but yet they weigh more than the sun, 1.5 times to 2 times the mass of the sun. Imagine squeezing that into a city like Hong Kong. That is how dense these objects are. My favorite analogy is that if you took every single person on Earth and you smushed them into a thimble, like the kind of thimble you would wear on your finger, that's the density of a neutron star. Every person on Earth in a thimble. Not very COVID safe, but it's a good analogy. So there are about 3,500 of these pulsars known now, and most of these live within our own Milky Way galaxy. They're very faint pulsars, so it's really difficult to detect them outside of our own galaxy. We know of some of them, like Matthew said, in the small and large Magellanic Clouds, but we haven't found any outside of those. And because Matthew gave me this, I am going to try to demonstrate the pulsar. So this is a flashlight. So imagine this is the pulsar beam. And I've never done this before, but I'm going to try. And so as the pulsar spin, I'm going to put this, I'm very clumsy. The first thing I did with my Shaw Prize was drop it, break the case, rolled under a table last night. So let's try not to do this. So let's make a pulsar. So every time the pulsar spins, this beam produces, well, it's always producing the radio waves, but we see a pulse of emission every time it spins by us. I'll go the other way, just for good measure. Okay, that didn't go so badly. That was okay. Okay, so we're introducing pulsars. You might wonder, why are they talking about pulsars? This is supposed to be a fast radio burst. There's a couple important reasons we are talking about pulsars first. One of those is this really interesting feature that we first learned about from studying pulsars that is going to be incredibly important to the fast radio burst story. And that is a phenomenon called dispersion. So Matthew talked about space and the stuff between stars and the stuff between galaxies. One of those things are electrons, right? So space is filled with electrons. The interstellar medium, or the space between the stars and our own galaxy, is filled with electrons. And an interesting thing happens when a radio photon passes an electron. It interacts with the electrons, and there's an effect called dispersion. So if a source emits light at different frequencies at the same time, when this light passes by the electrons, and radio light specifically, we don't see this effect for optical light, the lower frequency signals are delayed more than the higher frequency signals. And we call this a dispersion sweep, or a DM sweep. So for a pulsar will emit all of its radio waves, right, in this pulse at the same time. But when it reaches us, the radio emission at the lower frequency, so this is radio frequency here. This is like the frequency, you know, on your, does anyone have radios anymore? The kids are like, tuning a radio, what's that? But on your radio, you'd have, these are low frequencies, these are high frequencies. The lower frequency emission arrives later than the higher frequency emission. So we see this very characteristic sweep. This sweep is really important because if we see a sweep like this, we know that a radio signal has traveled through space because we see this special signature that tells us it has traveled through space. To detect pulsars, what we do is we measure this sweep and then we shift everything so it lines up and we add it all up and then we get a really nice profile like this. We sum over the frequencies and get this nice pulse profile here. Okay, one other cool thing that you can do with these dispersion measures is by looking at how big the sweep was, you can tell how far that radio pulse has traveled, right? If there's just a little bit of a sweep, not much at all, it probably was emitted from an object very close to Earth. If there's a really long sweep, then we know that it's come from somewhere very, very far away. So we can use this dispersion measure, or the amount of this sweep, to figure out how far a radio pulse has traveled before it has reached us. And so this is a model of all of the pulsars, and I'm going to try to be fancy. Let's see if I can ooh, it's so cool. Okay, so this is a model of all of the pulsars in our galaxy. This is the center of our galaxy here. This clump here is the sun, and the colors correspond to different dispersion measures. And red is low, so these ones are close to us. They have low dispersion measures, and blue is high, so the blue ones have higher dispersion measures. And so we can use this dispersion measure to figure out how far, you know, a pulsar is from a model of the electrons in the galaxy. So it's a really cool tool to locate these objects in the galaxy. Okay, so let's talk a little bit about pulsar searches. So the first pulsars were found using these chart recorders. This was also at a time, though, when computational speeds were increasing really dramatically, and you could suddenly do all these new amazing things with computers. So chart recorders were very soon left behind for computerized searches. There were searches in the 1970s that discovered a bunch more pulsars. So there were, a few hundred pulsars known by the end of the 1970s. And nearly everyone started to employ a technique called the Fourier transform. And basically, this is a technique that no longer relies on looking for the single pulses. It looks for the underlying periodicity in the pulsar signal. So not the individual boom, boom, booms that Jocelyn saw in the pulsar discovery, but the underlying periodicity. This was amazing. It resulted in a lot of new discoveries, including this incredible binary pulsar system with 2 neutron stars orbiting each other that resulted in a Nobel Prize in physics. So this Fourier transform was great. Lots of pulsars were found that way. However, astronomers knew that there were some pulsars that were found better or with higher significance by looking for their single pulses. And these are pulsars that emit giant pulses. So some pulsars, and in fact the pulsar at the center of this Crab Nebula is one of these pulsars, emit occasional very, very bright pulses, extremely bright, extremely narrow, sometimes 1,000 times brighter than the normal pulses. So we call these giant pulsing pulsars. And these types of objects, you could detect them better and farther away if you looked for the single pulses instead of the periodicity. So when I was a PhD student at Cornell, my advisor and I decided we wanted to try to detect pulsars in other galaxies, right? None had ever been found. We really wanted to try to detect them like very, very far away. And so we knew we couldn't look for the underlying periodicity. We needed to look for these single bright pulses. So we carried out a search towards M33. This is a galaxy called the Triangulum Galaxy. It's a local galaxy, local but still 3 million light years away. We searched it with a bunch of beams with this Arecibo telescope in Puerto Rico, looking for these single pulses. We didn't find anything. We knew it was a long shot, but we didn't find anything in this particular search. But we had developed this code that could look for single pulses from objects, right? So we'd worked to develop this code to look at data in a new way. And so when I arrived at Jodrell Bank as a postdoc, there was a very large survey called the Parkes Multi-Beam Pulsar Survey that had found a whole bunch of pulsars. And I said, why don't we apply this code to look at this survey and just see what we find in this survey if we look at the data in a little different way. And we found this new class of pulsars. We called them rotating radio transients, or RATs. And we knew they were real sources because we saw this very characteristic dispersion measure sweep, just like we saw in that plot before. Really, really bright pulses, this DM sweep, they were real objects. And the interesting thing was that they were very sporadic. They couldn't be detected in normal searches. There would be one pulse every hour even, right? So not every single pulse like we saw with Jocelyn's plot, but very sporadic pulses. And so there should be a whole bunch of these out there. And so because of this discovery, and by the way, I liked the acronym RATS because I had a pet rat named Wooly who I was very attached to. And here's a picture of Wooly. Okay, so so everyone started doing searches in this new way to detect objects, like these weird objects that you could only detect through these single pulses. And this is the kind of plots we would make when we wanted to look for these objects. So this is this dispersion measure. This is the amount of the sweep. You can kind of think of it as a proxy for distance, and this is time. And for these particular RATs, we would see something like this. So from this object, we saw 3 really bright pulses. The size of these circles corresponds to the brightness of the pulse. So 3 really bright pulses over like a 35-minute observation, which is very strange, right? So only 3 in all this time. And from the dispersion measure, we could figure out how far away these objects were. And this shows the same kind of thing we saw before, but the bigger points here are these RATs. And so for this particular object, we could say, given this DM, this object is, about here. It's about 10,000 light years away. Okay, so this is my last slide, and then I'm going to pass it over to Dunk. So this is where this story stood in sort of the mid-2000s. This is a plot of time scale for radio bursts versus luminosity, or brightness. And the green points are all the pulsars. These orange crosses are these RATs, which are really just more sporadic pulsars. They're not really much different. They just emit much less frequently. Here are the Crab giant pulses that I talked about. Here are Crab nanoshots, so extremely narrow nanosecond pulses from the Crab. But what you'll notice here is there's a lot of empty space on this diagram. Lots of space up here, space in here and here. And so in the mid-2000s, it was clear that maybe if we kept searching data in this way, looking for more of these single pulses, we might start to fill in this diagram a little bit more. And Duncan is going to tell us about that.
Okay. Thanks very much, Maura and Matthew, for giving us all of this information about the story. And it's really kind of setting it up for talking about how it unfurled. And so I'm going to talk about the discovery of what's known now as the Lorimer burst. I didn't name it that myself. It was one of those things that just sort of caught on over time. And it's really it's the first example of what we now call fast radio bursts. So in 2006, Maura and I left Jodrell Bank and moved to West Virginia. And here's a picture of us that summer, holding a 9-month-old baby who's now taller than I am. And yeah, time really flies. And we've one of the things that we really got to work on straight away was getting students involved in new projects. And the fastest way we could do that was to give them data that already had been taken, rather than go out to the telescope again and collect some more. As Maura just mentioned, we were really interested in looking for individual pulses, possibly rats or giant pulses beyond the Milky Way. So we searched the existing data, and in this particular case, we were very interested, and whenever I look, which one is the pointer again? I'm sorry. The little, oh yeah, I can never see the red dot. Oh, there it is. Okay, so we were interested in the large and small Magellanic Clouds, remember the satellite galaxies of the Milky Way that Matthew talked about. And shortly after we arrived at WVU, the student here, Ash, approached Maura and I asking for a project, and we had a number of students that were working on different things. And Ash's project was to look at data that had already been collected in the Magellanic Clouds to look for rats. A little bit of a story about the data. It had been collected in the early 2000s, about 2001 to be precise. It had just been published in 2006 as part of a general pulsar survey by the group listed here, including one of our collaborators on the discovery paper, Frony. And it used the Parkes telescope that Matthew introduced you to. In particular, it had a really nice feature of the telescope, this multi-pixel camera here. If you look at this little honeycomb, it has 13 holes in it. So it's a 13-pixel camera. Not quite as impressive as your cell phone, but for 21-centimeter radio astronomers at the time, it meant that you had 13 Parkes telescopes looking at different positions on the sky. So here's what happens when you look at the small Magellanic Cloud. You can see it being traced out here. And this is just one of those footprints of the receiver on the sky. So it allows us to cover lots of sky very efficiently. And this is the receiver being hoisted up into the cabin prior to operations. We got to work on these data, and we made plots in the way that Maura just described for us, where we have time running along the x-axis here. So we've got a couple of hours of data over a couple of hours, 7,000 seconds. And then remember what Maura was saying, dispersion measure, or distance you can think of really, going up the vertical axis here. And these are individual pulses from a pulsar above the background noise. And you can see that they're all occurring at the same height on that diagram. And that means they're coming from the same source. So again, you think of them as these. I'm not quite as adventurous as Maura, so I'm not going to pull this around. But you can remember that rotating lighthouse model. Those are the individual pulses coming from the pulsar in this case. And this was one of the pulsars. I forget which Magellanic Cloud it actually was in, but it was a pulsar that had already been found, and it was validating our search process. But the previous 14 pulsars that were already known in the Magellanic Clouds had all been found using this Fourier transform technique. So we were trying to look at the data in a new way, looking for individual pulses. And remember very clearly one day that Ash came into the office and showed me this plot here, where we had this really bright pulse. Remember, the size of the symbol here is proportional to the amplitude of the pulse. So you had something really well above the noise. This is just the background noise down here. You know, it's kind of sticking out like a sore thumb, as we would say. And we thought, wow, this is amazing. It's like, it's got this really high dispersion measure. It looks like just an individual pulse. And it only happened once in our over 2-hour observation. And then we started looking at the value of the dispersion measure. It had a value of 375, which was much greater than the value. Here are the dispersion measures of the individual pulses, some of the ones that were known in the small Magellanic Cloud, much greater than those. And then we looked a little closer, and we realized that, in fact, it was collected in a pointing, here's the footprint, that was actually a couple of degrees south of the small Magellanic Cloud. It's just the function of the way that the galaxy was covered by this technique meant that you had some extra pointings on the edge that were just looking out into the universe. And so we'd really kind of stumbled upon this thing. The pulse was actually detected in, shown here in 3. There's actually an additional detection. So 4 out of the 13 beams, which means and it's localized to somewhere around here. So we had this really unexpected signal at a dispersion that was much greater than the Milky Way. It seemingly had nothing to do with the small Magellanic Cloud. It was just looking out into the universe. Here's just a little close-up of the signal. A little bit later, a couple of months later, Matthew and I made some plots of this nature where we looked at the dispersion sweep that Maura was describing, and we kind of saw this behavior for the first time. And this was again just such an eye-opening moment for us. We saw this thing that was looking just like the dispersion that we see in pulsars, yet it was just coming from the distant universe. Interestingly, our software that helps us try to combat interference actually removed the strongest detection initially of this burst. This beam number 6 here, the pulse which is closest to the position of the source, it was so bright that it saturated the digitizers and the electronics in the receiver, and the system just flagged that's clearly interference. And so fortunately we had these additional detections that alerted us to the fact that the pulse was there, but then when we recovered that deleted detection, we saw, wow, this thing is really, really bright. So we had this sort of conundrum on our hands, something that we'd really never seen before, where we're apparently looking at a source coming from well beyond the Milky Way, which is over here in this schematic, perhaps from a host galaxy over here, and traveling towards, ultimately towards the Earth. And this little panel down the bottom kind of gives you a little picture of what happens to the pulse as it travels to the Earth. When we made some estimates of the distance based on the dispersion, in this case, based on our understanding of the intergalactic medium at the time that would be causing most of this dispersion, we came up with an estimate that it could be as far as 3 billion light years away. And for us pulsar astronomers, that's quite a big number. It's a big number for anybody, but we really weren't used to thinking of objects that far away. And it's, it's often as astronomers we get really caught up in the weeds of our observations, and we kind of forget that the amazing timescales that are involved. Anyway, a quick kind of walk through here is that the pulse is emitted at all frequencies at the host galaxy. 30,000 years later, it reaches the edge of the galaxy. It's dispersed a little bit, and then the next 2 or 3 billion years, it travels across a good fraction of the universe and arrives at the edge of the galaxy about 30,000 years ago. And finally, on 24th of July 2001, it arrives at the Parkes telescope. So it's we've really kind of stumbled upon this this singular event. And when you put it on that diagram that Maura just showed you a few moments ago, you see it's all the way up here. Its luminosity is about 1 trillion times greater than the rats, and it's just sticking out there in this parameter space, kind of screaming out like, "Here I am! I'm a prototype of a new phenomenon." And that's what we were gradually sort of coming to terms with, that we'd found something that was genuinely different from anything that had been seen before. So when you estimate the distance, and I want to stress this is still an estimate here at this point, we got this 1 trillion times more luminous source estimate, and roughly speaking, it's about the amount of energy that the sun puts out in a month. But our source here was only on for 5 milliseconds. So it was doing this on it was putting out an insane amount of energy on an insanely short period of time. So something very new. I'm not going to read the abstract of the paper. We just put this up here just to say how proud we were of this paper that we wrote up. We went through a number of tests of the data. We went back to the telescope. Matthew spent many hours looking for more pulses from the source. We never saw any further bursts from that spot in the sky again, nor, as far as I know, has anyone else seen anything. And so for that particular event, it only seemed to have happened once. And we made some bold estimates, some bold claims from that paper, most of which have turned out to be correct from the subsequent work. One of the things that we came across and really put forward was that we're only looking at a very small patch of the sky here. And that means that over the whole course of the experiment, we can miss all the bursts that are going off over the sky. And so what we really are seeing, although we only see one event, the total event rate of similar sources of this new phenomenon over the whole sky could be something like a couple of hundred bursts of this magnitude every day. And so again, it was all of these facts were very, very staggering. We had this very bright, distant object that was potentially going off all over the sky. So we had really some interesting thoughts going on in this paper that we presented. Because of its pulse width, only 5 milliseconds, it couldn't be something as big as a galaxy that's 100,000 light years across. It had to be something more like 5 light milliseconds across or smaller, that's able to produce what we call coherent emission along the line of sight, like a pulsar can do. So something like about 1,500 kilometers in size or less, a very small object. So perhaps one of these white dwarfs or neutron stars, but something compact, not a huge star or certainly not a galaxy. So we were thinking about different types of sources, in-spiraling neutron stars, pulsar-like objects, or perhaps magnetic flares from extremely strongly magnetized objects. We'd pretty much ruled out the possibility of terrestrial signals at that point. We'd carefully gone over this signal and looked at its properties, and everything that we saw was consistent with an astrophysical object. But we always have to have in the back of our mind the the possibility of interfering sources, which do make one more appearance in the story. Before I conclude my chapter, I just want to mention how this is sort of gradually trickling into the human psyche these days. Fast radio bursts appear in chapter 5 of this book on relationships that you might want to pick up next time you're at the bookstore. It tells you a little bit about that. They are also, Lorimer Burst is also the title of a German instrumental rock band that my sister-in-law here in the audience went to visit one of their concerts a few months ago and surprised them by telling them that they were she was related to one of the discoverers. And so that you might want to check them out as well there. And so it's becoming an interesting part of our culture. But back to Matthew for chapter 4.
All right, I might pick up the pace a bit because I sense that although it's been a beautiful talk so far, we're only halfway through. So I'm going to talk about the discovery of the cosmological population of the radio bursts. Having one is great. Publishing it is kind of brave. And in fact, the paper got rejected by the first journal we sent it to because they said, come back when you got more. That would have been a long time. One of my first students was Sarah Birks-Bloor, and her job was to look through all the other surveys that already existed for other examples of bursts. And I was at Berkeley one day and I got an excited email that she said, I found another Lorimer burst. And I went, whoo, this is awesome. And she said, and it's in all 13 beams of the receiver. And I thought, that's not so awesome. And I explained that things in the near field would appear in all 13 beams and things in the far field would only appear in a few. And so what she discovered was something very close to the Parkes radio telescope. Maybe it was lightning, maybe it was something reflecting off an aeroplane, or maybe it was something else. And so she named these things the peritons, which I think means a sort of a mystical beast of unknown origin. And I was a little bit worried because the dispersion sweep of this interference that she was seeing, it wasn't as nice and smooth as the Lorimer burst. They only make them with great quality for the first one. But this was kind of blotchy, but also kind of terrifying. Was the Lorimer burst just a sort of a more perfect version of this local interference? And if you actually looked at these peritons, they were blotchy, or they were sort of had all the power up here, or they had a little kink in them. And maybe we just got like some version of this, and you could see them in all 13 beams if you do what we call de-disperse, which is like integrate the signal along this path. And I looked at this and I was kind of scared and a little bit worried that maybe our science paper was not about something that was actually in outer space. But it did look so good, and the first night I saw that sweep, I couldn't sleep because I was so excited. So I really wanted it to be real, but I'm a bit negative in my outlook on life sometimes, and maybe I'd had too many doubts. But it took 5 years for anybody else to find one that looked kind of decent. And Evan Keen's a colleague of ours and used to work for me as a postdoc, and back in 2012, he looked through the same survey that Maura had found the rats in, and right here in the plane of the galaxy, he found this dispersed pulse, which looked really, really good. And if you look here, it's like doing its 1 upon nu squared thing, but it was kind of near the galactic plane, and maybe there was some H2 region of ionized gas or something. So this was a little bit inconclusive. And fortunately, a lot of my friends, or pulsar friends, and I had discovered or decided that we would survey the entire sky for neutron stars. And shortly after, we decided we would do that with new digital instrumentation that could do many more frequency channels than we'd done before. We started the High Time Resolution Universe Survey, looked at the whole sky, and Dan Thornton was a PhD student at the University of Manchester, and he was doing what was called the Lorimer burst search. But they were kind of waning in popularity, and the number of believers, and we have the prophet here, thank God, who refused to give up. But Dan was looking, and I think he was a little bit unmotivated and struggling to get progress. And his supervisor, Ben Stappers, just said, set a really high threshold and see if there's any Lorimer bursts. And These are all the pulsars that the survey had found. So it was finding lots and lots of pulsars, but it wasn't finding too many Lorimer bursts. And Dan set a very high threshold and found a 50 sigma burst. And motivated by that, he was more optimistic about looking at his data and his PhD in life in general. And he soon found another 3. And we wrote another science paper, so the same journal 6 years later, announcing the cosmological population. And we decided we needed to call them something. They couldn't all be named after Dunk. So I thought fast radio burst would be good. There was always something called a gamma ray burst, which was a GRB. So we just went back in the alphabet one. And I thought, GRBs are cool, so maybe FRBs will be as cool. And so we wrote this paper, and we showed that not only were they out there, they were actually fainter, and that was a great relief, because if you can see a really bright thing at a certain distance, if you put it 5 times further away, it should become faint, and you should still see it. And we'd actually found, one bright one, that was good, you could convince yourself it was real, but another 3 faint ones, and soon we'd found 10, and the population was fine. And we worked out they should be at a cosmological redshift of about 0.5 to 1. This means the universe was about half of its current age. And we also realized that if you could get the distances to the galaxies, you could actually work out how many electrons there are in the universe, and you could weigh it. And now we're talking some serious science applications and reasons why you should care about fast radio bursts. So this was his best burst, and this is majestic, and maybe after the talk you can come and do this, but you look down there and, oh God, it's just the stuff of heaven. And because it was digital filters, this sweep is absolutely perfect, and if it was real, it should get fatter by a certain amount at low frequencies due to scattering, and everything just fit perfectly, and I was really, 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 really happy. And if you plot where their dispersion was compared to how many degrees off they were from the galaxy, these are all the pulsars, the blue dots. These are the ones in the large cloud and the small cloud. That was Lorimer, and now there were these green dots. And so maybe there was a whole population of these things out there, which was really exciting. And I think it re-energized the field. But they were all still found at Parkes, which is a little bit worrying. How come other telescopes couldn't find them? And then along comes FRB 121102. This is in 2012 on the 2nd of November, I think. And this source, and you can see M. McLaughin and D. Lorimer here chiming in with using this telescope. And they found their own fast radio burst, and again, it looks nice, although it kind of faded out in some of a mysterious way. We think we understand that now. It's about side lobes. But this was found with another telescope, and when Laura actually gave her talk and I was present in the audience, I wanted to leap up and give her a huge hug for finding something that would validate our own discoveries at Parkes. And there's Laura. And she was at Jodrell Bank in 2013 and revealed that this had been discovered. So we started finding lots of bursts at lots of different telescopes. Some were stupendously bright, and the global population was alive and well. But we didn't know whether they were coming from a long way away still or not, because we didn't know the galaxies they were coming from. We actually worked out ways of buffering the output of the digitizer and getting a finer look at these things, and they weren't just a single pulse, they're actually comprised of this microstructure, and that's a hint about their origins, which we might learn a bit about later. But Whale Farah made these observations only about 5 years ago. And then finally, Emily Petroff and Evan and John Sarkissian worked out that if you opened a microwave at Parkes, it would give off a periton. And so we knew the source of the peritons. They actually clustered around lunchtime, which was a strong hint. And almost none of them ever happened at night when the visitor centre was shut. And so this was also helping to put together the pieces of the puzzle. And I'll hand over now to Maura, who's going to talk about repeating fast radio bursts.
Thank you, Matthew. Okay, so let's continue with our story. Not that way, this way. Okay, so I was part of the team that had discovered that burst with Arecibo, and of course we wanted to see might there be any more bursts coming from the same position in the sky? So just like we did with the Lorimer burst, we kept re-observing that same position again and again and again. And one day, I received an email from a graduate student who was working on this project. And he said, yeah, the observations went fine, everything's good, but a minor point of interest, I've detected more bursts from this original fast radio burst that was found with Arecibo. And we all laughed, because this was not a minor point of interest, this was a complete game changer, because we had discovered the very first repeating fast radio burst. All the other ones, there was one pulse, and that was it. No more pulses were ever detected from that position on the sky. And here we had found multiple bursts from the same position. This shows where these bursts were coming from. The important point here is just they were all coming from roughly the same position in the sky, so from the same source, not just coincidentally similar looking things from different objects. The same object was emitting multiple bursts. And here are pictures of these bursts. The dispersion has been corrected for. This is frequency versus time, so you see straight lines. The important point here is they all look kind of different. There's a lot of diversity. The shapes are kind of different. Some are really broad, some are narrower. Some have two components. Some are brighter at the low frequencies, some are brighter at the high frequencies. And this was very exciting. It opened up a whole new realm of what the heck are these things, because they're repeating and each pulse looks a little bit different. So there's some very interesting astrophysical phenomenon producing these bursts. The other amazing thing about the repetition, in addition to sort of the implications for the astrophysics, is that now that we knew that it was going to go off again, we could sit and look at it with a different kind of telescope called an interferometer that has excellent spatial resolution to tell us exactly where the burst is coming from. With the big telescopes like Parkes or Arecibo, these single dish telescopes, you can't really tell exactly where the burst is coming from. They have very poor localization. But we sat and looked at that position with a telescope called the Very Large Array in New Mexico. And this is an impression of that telescope. It's a bunch of single dishes. And that gets you much better resolution on the sky. And lo and behold, we detected one of these bursts, and we were able to localize it to a position on the sky with very high accuracy. And it was associated with a galaxy. And so once we knew it was associated with a galaxy, first thing is, of course, it was definitely astrophysical, right? The chance of some kind of, random interference or anything not coming and not being associated with a galaxy would be very small, so we knew this was an astrophysical source. And we could use this tool of redshift that Matthew mentioned briefly earlier, now that we knew that this was a galaxy, to figure out exactly how far that burst had traveled, exactly how far away this galaxy was. The basic idea of redshift is that we know that our universe is expanding, and as our universe is expanding, it basically drags the wavelengths with it. So wavelengths get longer when they travel from larger and larger distances, and we're not going to talk about the equation or anything, but this redshift, this z thing, tells us how far away a photon has traveled through this expanding universe. Okay, so this is a picture of the galaxy from which this burst was emitted. It looks very unremarkable. It's right here. That's the host galaxy to this fast radio burst. It turns out it came from a galaxy about 3 billion light years away. And we were very surprised at first when we looked into this galaxy more. This was a very small galaxy. This looks like a big number, 50 million solar masses, but this is over 10,000 times smaller than the Milky Way. So a small galaxy. There was something called a huge rotation measure. This is a measure of the magnetism that this burst has traveled through. It was born in a very magnetic, very energetic environment, so that was a clue as to the origin. And this galaxy also had a very high star formation rate, so that means it had a lot of young stars. So these were very important clues that these might be coming from, most likely, massive neutron stars. The remnants of massive stars are neutron stars, as Matthew mentioned. So stars that don't live very long and then blow up in supernova explosions and produce these neutron stars. So we had a pretty good idea of the sources. We know these need to be coming from something very small because they're very short, something very young. So neutron stars. So that was exciting. And then people started finding more and more bursts and also detecting more bursts from this original repeater with other telescopes. And a lot of interesting things started to pop up over the next couple of years of research. One thing that was really interesting is some of these fast radio bursts seem to show periodic emission. So for instance, we detect like a bunch of bursts, then nothing, a bunch of bursts, then nothing. There was a new fast radio burst that seemed to show about a 16-day periodicity. The original repeating fast radio burst, this Arecibo one I just talked about, seemed to show like a 157-day periodicity in its emission. That was really weird. The other thing we started to notice is that bursts had a really wide range of morphologies and shapes. Some of them showed very small structure, so like multi-component structure. Some of them, and this is the original repeater, we saw this really weird structure with multiple components fading in and out at different frequencies on very small timescales. And a ton of these repeater bursts were detected. The 500-meter telescope in China, the FAST telescope, here's a picture of it here, detected 1,652 bursts from this original repeater. So we had a huge amount of data, and we went from the situation where we first found this Lorimer burst to not knowing anything about it because we just had one, to actually having a plethora of data and so many discrepant properties that it was then really hard to tie them all together into a single consistent picture. One of the models that was brought up to try to explain this 16-day and 157-day periodicity was a binary system. So a 16-day periodicity is much too long for a rotating neutron star like the pulsars, right? Like they're rotating at second periods. 16 days could be in orbit, however. So this is an example of one of these models where you might have a neutron star. Maybe it's traveling close to a very massive star called an OB star, and these bursts are stimulated by interactions with the wind from this OB star. And there's lots of different models like this. And at one point, this is fun, but I'm not going to do this for too much longer. So at one point, there were more papers on what these fast radio bursts could be than there were fast radio bursts themselves. So theorists were very excited about this. Lots and lots of different models for the emission from these objects. And just to show, every telescope in the world started detecting these objects, many different bursts, lots of different phenomenology, very broad bursts with lots of very small timescale emission, very, very narrow, bright bursts, weird frequency structure, all sorts of things. I want to just talk a little bit about this burst down here. So this is a very bright burst, very short timescale, detected with a very small telescope called the STARE telescope. And this is a tiny telescope, but a very bright burst. And this was a really important discovery. So this burst was actually detected from an object that we already knew about. So this telescope and a telescope in Canada called CHIME, this is the same burst detected with these two different instruments. This burst came from something that we knew about called a magnetar. So magnetars are very highly magnetic neutron stars. We had already known about them. They're very bright X-ray and gamma ray emitters. And we saw something that looked like a radio burst, like a fast radio burst come from one of these magnetars. So this was really exciting because this was a definitive clue that maybe these very highly magnetic neutron stars could produce these radio bursts. This thing looks really bright, but it's much more nearby than the fast radio burst detected from many other galaxies. So this thing has about the energy that the sun emits in, say, 30 seconds, not a whole month. So it's really bright, but not quite as bright as those other objects. But it showed that these highly magnetic neutron stars, there was some possibility that they could be producing these fast radio bursts at cosmological distances as well. And I'll just briefly mention that the 2021 Shaw Prize was given to Vicky Caspi and Chris Okubilatu for their work on these highly magnetic objects. So there's a really nice tie-in with the work that they did to understand these magnetars. Okay, so I will pass it back to Dunk.
Okay, thank you very much. So I'm going to round out the story with just a few highlights from the last few years. So CHIME, as Maura just mentioned, is a telescope in Canada that turns out to be excellent for fast radio bursts. It was actually developed for a different purpose, but for fast radio bursts, it has a huge field of view, about 200 square degrees of the sky, much larger than most other radio telescopes that had been used to that date. and it observes the sky overhead once a day. It is finding lots of sources, about 3 FRBs every day it's been finding, and it's been on for several years now. It has a catalogue of several thousand FRBs that are about to be released to the general public. So there are a lot of repeating sources there. About 10% of all FRBs now repeat, and CHIME is a very good instrument to do that because it sees the sky every day. So we're starting to build up statistics on fast radio bursts now. We're getting larger and larger numbers, and so there's lots of interesting things coming out. One of them is in a nearby. One of the repeating sources is in a nearby spiral. It's relatively speaking rather close to us, has a low redshift, so that's interesting. It's this spiral galaxy here. It's out in the outer spiral arms, so where you would have sort of magnetar-like stars, magnetar-like progenitors being formed. But another one is in a much older stellar environment that Matthew mentioned, these globular clusters, where no star formation has happened in recent memory, and they're much older stars, and so we're starting to get a picture now where FRBs are coming in a diversity of environments. The other thing that we're learning is that FRBs have different morphologies. That is, that the pulses look different for different types of FRBs. And just very briefly here, I want to get across the message that the 10% or so of FRBs that repeat look rather different. They're generally broader, they have broader pulses, and they don't occupy the full band. This is the frequency band versus time plots that you've been seeing. They generally occupy just a part of the band, whereas the one-off sources occupy the whole band typically. And so there's this dichotomy between the one-off sources, which are the majority, and then the repeaters. ASCAP, which is the Australian Square Kilometre Array Pathfinder in Western Australia, is also a powerhouse in this industry because it's able to localize many FRBs to their host galaxies. It often finds them in star-forming galaxies, very rarely in the red and dead galaxies that Matthew introduced earlier. But in any case, the picture here to get across is that FRBs are coming from a variety of environments. You can see them all over the sky. This is a map of FRBs on the sky. It's a biased map because some telescopes are much better at detecting FRBs and much more sensitive in some directions compared to others. This is the CHIME area where it's most sensitive, for instance. But when you correct for those biases, you find that FRBs are basically a uniform population all over the sky. Just to close out now with a couple of sort of cosmological applications to look for these missing baryons that Matthew talked about, to measure the electrons between the galaxies. FRBs are really unique probes at doing that, so they offer sight lines out to multiple sources. And basically by mapping the dispersion measure versus redshift, you can directly measure those electrons. And the first team to do that was led by J.P. McCarr, who sadly passed away in the year 2020, just after the landmark paper describing this relationship. J.P. was a real leader in the radio astronomy community, and he is very definitely missed. Some of the other applications, I just want to highlight one here. FRBs turn out to be a potentially good probe to measure the expansion rate of the universe, which is often known as the Hubble constant. Here's just a map of, or a graph of the Hubble constant versus time. And going back to, well, it actually dates back to a century ago when Edwin Hubble first discovered that the universe was expanding and first measured that expansion rate. But the expansion rate has been measured more and more precisely ever since, and here are a number of measurements over time here. There is something of a tension between different techniques. that is one of the things that is trying to be resolved within the astronomical community right now. Whoops. But FRBs kind of offer a way to help with that tension. They can potentially offer an alternative view of this. Here's the current estimate or measurement of the Hubble constant, I should say, using FRBs. And it's about as good as the Hubble Space Telescope was over 30 years ago. And it will get better as more and more FRBs are found and included in this analysis. So again, it offers a new spin on cosmological science. The final result I just want to show is just really hot off the press in the last few weeks or so. This is an FRB at a redshift of 1, so it was emitted when the universe was half of its current size, and that means that the burst has traveled approximately 8 billion light years to reach the Earth. When you work out the energy that's associated with that, it's incredibly luminous. It's putting out in a few milliseconds about what the sun does in 16 years. And so this implies that FRBs are potentially detectable in the high redshift universe, and that is very, very exciting indeed for a number of cosmological applications. And this is just another quick plug for our friends using the FAST telescope, who are doing amazing things with these repeating sources. They're finding thousands of bursts, and they're able to see that the FRB-like bursts are occurring basically at random spots around the neutron star in a magnetar-like model, compared to the regular radio-emitting pulses. And so we're starting to get some clues as to the radio emission of these sources. Just to close out now with a couple of shots that Maura and I took yesterday on our run, the look left and look right signs here in Hong Kong. Something that we all learned as children to carefully look left and right when you cross the road. Very good advice. It's also very good advice when you're looking at this diagram here. Look how much we filled in this parameter space here with the fast radio bursts. But there's a lot of white space to the left and indeed to the right that can still be explored, and those are among the targets for current and future instruments. And so this story is really only just getting started. There are more sources to explore. We really have so much more to learn, and that's evidenced by all of the many open questions that are among us in this field. Many of which we've talked about throughout this talk, and perhaps we can come back to in the Q&A. So I just want to close with a number of thank yous. Firstly to our collaborators, Froni Crawford and Ash Narkovic, for helping us getting started in this story. All of our students that Matthew, Maura, and I work with around the world to do on this and other projects. That's the reason we get out of bed in the morning, is to go and work with these wonderful people and to discover new things. And thank you to a number of organizations that are listed here. The Shaw Foundation for really shining a light on this work. We're really thankful to them for that, and really happy to be here to tell you this story. For Maura and I in the US, we receive a lot of support from the National Science Foundation, Matthew from the Australian Research Council. We receive funding from the Research Corporation for Science Advancement. Sounds a bit like a commercial at this point. West Virginia University has been very supportive to Maura and I, as is its local NASA space grant. Matthew at Swinburne has had amazing support there, including our colleagues at the Australian National Telescope National Facility and NRAO. So thank you to all of those organizations, and indeed you as the taxpayer and the driver of much of this science, because it really, joking aside, what we do as scientists is only possible thanks to the support we get from these organizations, which is often driven by the support of you. And so we love doing this work. We love to tell you about it, and thank you for indulging us this afternoon.
Well, thank you very much. Thanks to all three, Matthew, Duncan, and Maura. We're running a bit late, but I do think that we should take some time for some questions from the audience. Sure. There's the microphone.
So how do you read a sweep graph? How do you read it? Because I kind of got a bit confused on reading the frequency and the time bit.
See if we can find a good example. One in the middle.
You're on. So.
Okay, yeah. So what you're looking at is radio frequency. So that these are the frequencies of the radio waves on the sky that the telescope is measuring versus time. So we have an instrument. Oh, thank you. That's much better. And I want to take a look at this. So we have an instrument known as a spectrometer that is providing digitized versions of those signals. And really the main thing to look at here is that curve, and its mathematical form is parabolic. So it goes as 1 over frequency squared. The highest frequencies arrive first because they're traveling faster through interstellar space relative to their lower frequency counterparts. So when we say sweep, it's this thing here, and what it is, it's a delay from high to low frequencies. So the bigger the delay, the more electrons the signal has interacted with, the farther it is away. So it's a way of estimating their distance. So that's helpful.
Yes, and also I wanted to ask, what's the difference between RRATS and dispersion? Yeah.
So the rats, the difference between the rats and dispersion measure, or is that the question? Yeah. So the rats were the kind of first class of sources we detected with this new algorithm that looks for single pulses, and the rats had dispersion measures that are much lower than the fast radio burst. So the dispersion measure is basically just it's the magnitude of this sweep, right? So the dispersion measure tells us the slope of this sweep and how far away something is. So for those sources, the dispersion measures place them within the Milky Way galaxy. So they emitted these bright bursts, but they were very local within our galaxy. The fast radio bursts have higher dispersion measures, which means more of a sweep, which means they traveled through way more electrons, which means they're coming from much, much further away. So the rats are kind of just like pulsars. They're just much more sporadic. Whereas the FRBs are a very different kind of source, almost certainly still from neutron stars, but a very different emission mechanism than the pulsars and the rats.
Thank you so much, all three of you.
Okay, other questions?
Thank you very much for the great talk and this introduction and the discovery of the fast radio burst to open a new research area for this field. So I would like to ask a rather hardcore questions. So Professor Duncan Lorimer, you mentioned a bit about the possibility to map out the missing baryons of using fast radio bursts. So I will expect that if you are trying to map out the missing baryons, you also need to map out the neutral hydrogen instead of just the electrons. So I will expect there is a synergy with the fast radio bursts and also with intensity mapping experiment. So I think this kind of effort is ongoing. But would you like to comment on a bit of the bottleneck or the foreseen difficulties for this kind of approach?
Well, I think really it's the main bottleneck right now is getting a larger sample of FRBs with redshifts. So we've got right now about 40 of them that have some measurement of redshift that's nothing to do with the dispersion measure. But telescopes now are coming online that will allow more and more of these to be found, where we can, a few years from now, we'll be in the territory of hundreds and soon enough thousands of spectroscopic redshifts that are measured. So I think that will help tremendously. The other challenging thing to do with Actually, yeah. So one of the challenges that you have to do to make those inferences is to estimate the amount of dispersion that has come from the host galaxy, and so that requires a significant amount of optical follow-up of the hosts as well. And so these collaborations quickly involve large numbers of people. But we know in principle how to do each of those pieces, and by studying the variance in the Maura relationship, we should be able to learn things about the distribution of electrons along different lines of sight.
Yeah, I might also add that if you're an atom between the galaxies, if you're like a neutral hydrogen atom, you don't stay neutral for very long because you get hit by a UV photon and you get dissociated. So we don't have to worry too much about all the atoms that we're not sensitive to because of dispersion, because there's a high enough UV photon flux that everything just gets ionized, which is great because then you can use FRBs without having to worry too much about what the ionization fraction is. Right in the middle of galaxies, it's possible for the gas to be protected from the UV photon because there's so many other atoms. So it's true that in galaxies, you have to worry about the neutral hydrogen fraction. But the number of atoms that are actually in galaxies compared to in between galaxies is kind of pathetic, which is great because then we can count the number of atoms, and the other thing's just a sort of a 10% effect, and 10% in astronomy is usually not too much to worry about.
Yeah, thank you very much.
And if you get them out to very high Z, you can also,
Right.
because you see the transition from more far ionized and fully ionized, that transition will show up. Sorry.
Yeah, so Professor Smoot was just saying, gee, if you could get something at Z equals 4 or a redshift of 4 or so where helium contributes, you could get a kind of a step function in the density. And
Tiny one, but yes.
yeah, we think we have enough sensitivity to detect FRBs that far out. It actually gets really hard to work out which host galaxy it's coming from because the galaxies get really, really faint. And there's some FRBs that we think are at Z equals 1, and even those ones we can't find the host galaxies. So going a factor of 4 further is at least a factor of 16 worse in brightness, so that's going to be tough. But when we build 30-meter telescopes or the European 40-meter optical telescope, maybe that'll nail one.
Your record redshift is 1?
1.
Yeah, we've got things with dispersion measures of like 3,000, and we think they're at probably Z equals 3, but they may not be. They might just be in a highly ionized area in a closer galaxy. The record for the host galaxy is Z equals 1. That was only published like last month.
Yeah, thanks for the great talk. I'm just curious, what's the prospect to observe the lensing of FRB in the future?
Pretty bad, because gravitational waves, sorry, not gravitational waves, fast radial bursts have such a huge span in luminosity, it's a bit hard to tell when it's lensed or not, especially if there's only one of them. And if you have a repeating one, we know they vary in brightness by about a factor of 1,000. If you could get one that went one way around a galaxy and another way, and there was like a month-long delay, that would be incredibly exciting. But we only ever look at a small part of the universe at once, and getting it both times would be kind of super lucky, but maybe somebody will get lucky one day.
Thank you.
There's one here.
Yeah, thank you for the great talk. And I'd like to ask, when you're using this dispersion measure to indicate distance, so does it lie on the assumption that electrons are uniformly distributed in the universe?
No.
Yeah.
No.
Yes and no.
Yes and no.
It depends on what scale, but maybe I'll let Maura elaborate and then I'll counter it.
Yeah, so there's Dunk showed this nice plot of all the different bits of the universe that the pulse is traveling through. So it'll travel through its own galaxy, then the intergalactic medium, then our galaxy, basically. We have a model for our galaxy that's definitely not uniform. There's more electrons in the pancake-like disk and fewer above it. The galaxy that the burst was emitted from probably looks similar, but we can't really model it because we don't know whether it's edge on or face on or whatever. We assume that the intergalactic medium electron density is constant, though. So we have a relation that converts, anyway.
I'm just going to add to it.
Yeah, okay. Yeah, so the model that we use for the intergalactic medium assumes that that is just a constant number of electrons per centimeter cubed, a very, very small number. But right now we assume just uniform with redshift, right? We have an expression for a particular redshift that'll give us a particular DM. But I think George would like to add to it.
The answer is, okay, since I'm interrupting too much.
Go ahead.
You can, in the early days, there were few enough of the fast radio bursts that uniform assumption was right. In fact, the intergalactic medium is pretty uniform, but it's going to have the irregularities the same way. Otherwise, we wouldn't have galaxies and clusters of galaxies. And so if you measure it, you'll have a finite width. If you make the assumption it's coming that way, you'll have an extra error bar in that direction. And by measuring that width, you can see it. It's just like measuring the scintillation and the other. There are extra phenomena, but you're going to have some extra width from the fact that some of these guys are in galaxies and they have the local dispersion measures. So you could integrate it out, right? But what it means is you want to have a lot of these so that effectively that source of error can be integrated down because it's going to be roughly Gaussian, right?
Yeah, I don't think Maura and I do disagree too much. This is our knowledge of our galaxy's electron density, and it's quite good. We know that the distant ones are blue because they've got high DM. It turned out prior to the discovery of the fast radio bursts, our knowledge of the Z distribution of electrons was actually pretty uncertain. And some of the ones we've found that we know are in other galaxies, our models say they should be in our galaxy. So we're still calibrating that Z direction. But as George said, on like cosmological scales, you go through so many voids and non-voids. You could get really unlucky and go through a galaxy and get a bonus 1,000 DM units, but it's kind of rare. And statistically, it'll wash out, we hope.
But you need to get a lot. You got to keep in business.
We're on our way. I mean, we should have tens of thousands of these things within, a decade or so. Something like that.
I have a question about those really intense and bright ones. Are any of those recurring, or what percentage of those really intense ones are recurring? And are those recurring, or are those really bright ones closer to us, or is there any enough data to show us that there's some sort of distribution, or because intuitively I would have thought that, we would have thought that the really intense ones are closer to us.
You've looked at this the most, probably.
I mean, it's true that you generally see the brighter ones at lower dispersion, but there's a big range around that. So we don't think that fast radio bursts are what astronomers call standard candles, that they're all emitting the same amount of energy. And so there's like a one-to-one relationship between the luminosity and the flux and the distance. And so there's a distribution in luminosities.
But, are those really bright ones recurring, or are they one-off events?
Most of those, it's my understanding that most of those points there are from repeated bursts at a galaxy of known redshift, of which there are relatively few. So they're kind of dominating that plot there. You can see that they're labeled localized FRBs, so that we haven't got that many localizations. They're mostly the repeating sources at multiple detections of a repeater.
I think we see really bright one-off bursts and really bright repeaters.
Yeah, I think on average the repeaters, I think there was a paper that they're just slightly fainter, but not like a factor of 100. And you can think of that being a natural selection effect. If you've got a repeater and it has some log n, log s distribution, there's lots of like faint ones for every bright one. So you're more likely probably to catch one of the fainter ones if it's above some threshold. But if you look at the repeater and say, what's the span of bursts, it's actually like this is an amazing graph. This is a factor of 1,000 in the logarithmic scale. And you know the reason Lorimer burst was so terrifying when we found it was a factor of 10 to the 12 times brighter. So there really is a tremendous span, but also within a repeating FRB, you get this factor of 1,000 internal range in bursts. And it probably, if we had a bigger telescope, it might even be a factor of 1,000,000 or so. But we just run out of sensitivity to see the fainter ones.
Any sort of indication or conjecture, or are there any commonly accepted view why this burst occurred, or the reason for this burst?
No.
I mean, they all involve neutron stars, the commonly accepted views. So the same thing that produces, pulsars, but it has to be something very different because they're much brighter. Most of the models involve magnetars. That's a very popular model because we've detected a fast radio burst-like thing from a known galactic magnetar. So magnetars are these neutron stars with very, very high magnetic fields. Exactly how the bursts are produced is still a really open question, but we think somehow the magnetic energy is getting converted into a radio pulse, so maybe some kind of magnetic reconnection event, something like that. But it's really a very open area of research right now.
Thank you.
Yeah, it might be some sort of random reconnection of magnetic field lines that has no particular periodicity or predictability. But it might also be seeded by interaction with a plasma. So in that model of the repeater, if it goes through some disk of material, that might stimulate sort of fast radio burst production for a little while. But these are very kind of hand-wavy models. And for 50 years, we've been trying to understand pulsar emission and failing. So ask us again in 50 years, I guess.
One cool thing, though, is we don't need to understand them in order to use them as cosmological probes. Just like pulsars, we don't understand them that well, but we use them for all these amazing physics experiments.
Right. So I have to say, here at HKUST, we had a student who's now graduated and gone to a prize postdoc in Canada, but a month or half ago or something like that. But we had a model, that Pawan Kumar and I had a model where these bursts were coherent synchrotron radiation, basically. You have the strong magnetic field, and you go through a burst of plasma, and the electron, because of the relative speeds, they're relativistically moving, but as a group, because they're emitting at a wavelength, and then it's boosted forward. And the prediction there was it'll show up great in the radio, but it'll poop out before it gets to the infrared, right? So a test of the model is you see fast radio bursts all the way up to the near infrared. And, we didn't see any, unfortunately. And he had to graduate, so we didn't need to say we were right or wrong.
So I think on that note, since time is running short, let's take this opportunity to thank Matthew, Maura, and Duncan again for spending time with us this afternoon.